So I'm about to log into my FreeBSD server. This is an ARM server running in AWS, and it's running FreeBSD. I've got the MicroPython executable installed in here. MicroPython. Somewhere. There is their MicroPython version 1.17. I just installed this from the FreeBSD package library. So I'm going to run this on some code, and my code here is called exploit.py. This code imports a dodgy library. We'll look at that in a minute. Then it sets up 2 byte arrays, tiny1, which is only 1 byte long, and tiny2, which is 7 bytes long. Inside the tiny 2 byte array, I'm going to poke some bytes to spell out the string hello. Then, as I scroll down, I'm going to print out the string as a UTF-8 string, so it should print out hello. Then I call the dodgy library, dodgy function, and supply the first buffer, tiny1. Then I'm going to print out tiny2 again as a string, and what I would expect to see is that tiny2 should again print out hello. But what really happens is that the dodgy library has modified the tiny2 string, even though it shouldn't have access to it. It's modified it, and so actually I get something different in tiny2. Let's run this and see what happens. MicroPython exploit.py. Oh, look, the first time when I'm printing tiny2, I do get hello, but the second time I've printed it, without explicitly modifying it, instead I get hack. The string has changed, and the reason for this is, if we have a look at the dodgy library, we'll see that the dodgy library takes the address of x, which is tiny1, the first byte array, and then tries to construct some kind of large buffer of 2,000 characters starting at the same address as x, which is tiny1, and then it iterates through this buffer looking for letters E and L. And if it sees them next to each other, that's part of the hello string. If it sees them next to each other, then it's going to replace those letters with these bytes here, which spell A, C, K, exclamation mark. So hello will turn into hack. So this is really dodgy code. This is actually modifying bytes in a memory area that it shouldn't really have access to. And this works just fine in the normal MicroPython on a standard conventional ARM machine. This is the AWS T1.micro. It's a Neoverse machine, which is running in the cloud. Now we're going to look and see what happens on Morello. So here I am on my ARM Morello machine. It's in a special case, but it's a standard ARM machine from the DSBD program, and I'm going to log in here as root with my password. Okay, so on this machine I also have a MicroPython. This is the MicroPython version that we developed at Glasgow, and PureCat MicroPython. So this has got extra protections in it for running code with capabilities. So I'm going to try and run the exploit code in here, MicroPython PureCat, with the exploit code, the same code that we had on the AWS machine, and I run it this time. Oh dear, what have I done wrong? I think I need to put / at the front, sorry. / and look, we see the first hello, but then we get the cherry protection error when we try to dereference using the restricted pointer from tiny1. Let's revisit our code and have a look and see what's happening. We've got our tiny1 array with tiny2 a little bit further down in memory containing the hello string. We have a pointer to tiny1, and in .g we somehow extend this pointer to point to tiny2 so we can modify the characters in the hello array. If we have a capability, then there's a kind of barrier that prevents us getting past the end of tiny1, so we can't access the string in tiny2. Thanks so much for watching. This was the Secure MicroPython Morello project at the University of Glasgow, funded by DASA. Goodbye.